So this is a high pass. After the high pass, you build a low pass filter. It's an active one. I think you already see that in the menu. The cutoff frequency is 1,000 rad per hertz. Remember, it's omega, it's not f. Okay, so choose the RC value that gives you this omega low pass filter corner. And then after that, you need 2 notch filters, each one tuned at 60 hertz. And the reason is that all the instruments are using power coming from 60 hertz AC signals. So even though you're using battery on your PCB, you still be able to see 60 hertz signal at the entire circuit output if you don't filter it at all. So that's why you need 2 stages of filtering to reject very large 60 hertz signals. That's the main amplifier and filter chain. Of course, you need the plus and minus 5 volt for all the op amps that you use. And that will come from a 9 volt battery. You have 2 9 volt batteries, and the way to get 5 volt is to use a regulator. These 2 regulators are different. One is for positive output, where the other is for negative output. Okay, choose the correct one. I think the connection is very simple. It only has 3 pins: input, output, and ground. So input is connected either plus 9 or negative 9 volt, and the output is connected to your op amp positive and negative rails. Okay, and this is something in the front. I think you don't have to include a simulation. Maybe this. So basically, when your circuit is ready, we'll either test with a actual EEG electrode that you can put on your head, or with a signal generator going through a resistor divider. So this will be considered as a test function, because if you never test the actual circuit on a PCB, you don't know what's going to happen. You don't want to put the electrode directly onto your head and try out the circuit. So you always want to test the circuit with a signal generator first. You use a signal generator going through a resistor divider, so you get a voltage level around 10 microvolt. It's in the range of 1 microvolt to 100 microvolt. Okay, and then you monitor what's coming out of your amplifier filter on the oscilloscope. You should be able to see a voltage around 100 millivolt to 1 volt, and if you do the Fourier transform on the oscilloscope, you will see a strong tone at DC and also the 10 hertz frequency. Okay. Yeah, so the only thing you haven't built is this notch filter. A notch filter is essentially a simple RLC series circuit. Okay, you can imagine at the frequency of at this notch frequency, these two will form a series resonant circuit, which means the combined impedance 0. So at that particular frequency, your output will be basically grounded. That's how you design a notch filter. In reality, because this inductor is too big, so you have to synthesize the inductor from the active op amp. And the way to do that is what's outlined in the lab manual. If you don't know how to derive the impedance of that particular circuit, you can come and we will show you. Yeah, so basically you have 2 weeks for the first part, and I think hopefully you can finish, but you can start laying out next week. Is there anything else?
Yeah. Okay. First of all, does anybody have any questions about what we covered just now? Because it is a pretty long process, and you have to make sure that all the stages work.
So the goal for today to have a working simulation?
No, the goal for next week is to have a working simulation.
Mm.
So you have about half of the time today and then the other half tomorrow. A couple other things to note is that if you look in your lab manuals, there is a list of footprint, or there should be a file on bspace. It is a footprint file, which means that is that right? Like, have you gone through the? Has anybody gone through the?
It's
okay,
for next week's layout, I thought. Or next week's layout.
But you,
the footprints don't really matter until like we're done with the multi-sim simulation.
right, but it helps tremendously if you just start with the right footprints in the multi-sim simulation in the first place. Because otherwise you have to go back and replace. Basically what a footprint is, you have these components, right, like resistors and capacitors and like op amps that you're putting into the multi-sim simulation. But these, the ones that we've been using are just generic resistors, so they don't have like a manufacturer or like a tag. But in reality, when we actually take this to the manufacturer and print a PCB, we're gonna want it to be fine-tuned so that we're using, or when we simulate this multi-sim circuit, basically we want to simulate it with the components that we're actually going to use, like solder into the board. So then we can, there's like, even like if you're putting in like a single resistor, there's like a bunch of different types of resistors that are manufactured by different companies. And we want to pick the footprint, like the tag of that resistor to match whatever resistor that we're going to use. So there is a zip file for that on BSpace. You download that, import it into Multisim, and then every time you place a component, you select the correct footprint that you want it to be. And the correct footprints are inside of the lab manual, or in the lab instructions. And the other thing is that if you try to build this entire circuit in Multisim, it's a very, very large circuit. Because, I mean, I'm sure you guys remember the instrumentation op-amp that's like 3 different op-amps. These 2 are going to require another op-amp, or 1 op-amp each. And then this guy's also an op-amp. So then you have a bunch of op-amps, all with power sources and a bunch of resistors. And it's one really big circuit. A way that you can mediate this is by creating these things called modules. And they're basically like blocks. And it'll basically look like this on your actual circuit. So then what you're doing is creating a little block. You can do it by going to place. In Multisim, go to place, and then do new hierarchical block. And it'll create a box that looks just like this. And what you can do is edit that box, and inside of that box is your actual circuit. But when you put it out on the schematic, it'll just look like this, so then it doesn't take up as much room. And you can kind of keep track of like the different stages. So instead of putting the entire circuit on one multisim like sheet, you can split this up into hierarchical blocks to do it part by part. And I think we're giving extra credit to people who can finish this like by this week, but I don't know if that's a feasible goal. You can like, unless you start it early, but yeah, you guys can try to like work really hard and see if you can get it done. But yeah, I think that's it.
Okay, yeah, I want to mention one thing is, after you build the entire thing, you need to do 2 simulations. One is one is an AC analysis, and the second is a transient. For the purpose of the AC analysis, just to look at the frequency response of the entire scene, you should be able to see a high pass corner, low pass corner, and a notch. Okay. Of course, I would recommend you to do the first AC analysis for each individual block. So you make sure each individual block performs the way you like, right? And the second simulation is transient simulation. So after you finish the entire scene, run a 1 second transient simulation with the input signal of 10 Hertz and a magnitude of around 100 microvolts. So then you should be able to see a pretty strong signal at the output. So yes, so for the first simulation, I would recommend you do it for each block.
Oh, and while I have your guys' attention, your labs 5 and 6s are graded on that table back there.
And also lab 4.
And lab 4 apparently. So if you guys could pick those up, that would be great, because I'm like calling them